is tangent times x plus y.
Is it the tangent of xy?
No, x plus y in parentheses.
Oh, excuse me.
Yeah. And equals x equals x.
Okay. So if we're going to implicitly differentiate this, are we going to find dy dx?
I'm sorry. I forgot something. You have to find the implicit differentiation and evaluate the derivative at a given point.
Okay.
What's 0, 0.
0, 0 here?
Uh-huh. Yeah.
All right. So we're going to find dy dx, correct?
Right.
All right. So when we implicitly differentiate, we're fine as long as we only come across variables that match our denominator. So when we do x, we can essentially do it explicitly. But when we do y, we're going to have to follow it with a dy dx. Okay? So you have to apply the chain rule to do that one.
All right.
What's the derivative of tan of u?
Secant squared.
So that would be secant squared of x plus y. That's the outside. What's the derivative of the inside?
Well, wouldn't it be 2 times y plus 1? Or, sorry, 2 times dy dx.
Just take the derivative of that. What would that be?
It's 2, right?
No?
Isn't,
what's... Take the derivative of that, which is 1.
Right.
Don't have to follow it with a dy dx.
Yeah.
Because I could follow it with a dx, which is also 1. That's why you don't need it.
Yeah.
Plus 1, but this one is not x. So I have to follow that with a dy dx.
Okay, I see.
So it's not 2, it's 1 plus 1 dy dx.
I see.
So 1
All right.
plus dy dx. That's the derivative of the inside. What's the derivative of the right side?
That's just 1.
Okay. And differentiation is like any other thing. If you have an equation, you can do anything you want to one side as long as you do it to the other. And that includes differentiate. As long as I differentiate the left and the right, I can do it. I can integrate it. I can take the log of both sides. I can do any of those exotic things. So now we have to solve this thing for dy dx.
All right.
Well, how do I do that?
So, well, I guess this is mostly where I ran into trouble.
Distribute it.
Now, I don't really know how you get rid of that 1 that's in the parentheses.
Just distribute the whole thing. In other words, I'm going to take this quantity here, multiply it by 1. And then I'm going to add to it that same quantity multiplied by that. With me?
Yeah.
That's all I did was distribute. In other words, just algebra.
Okay.
Okay. Let's keep going. Right. We're trying to solve for dy dx. So the next step is to take any term that does not have dy dx in it and move it to the other side. Well, that would be this term here. Okay. So now I've got secant squared x plus y dy dx equals 1 minus secant squared x plus y. If I lose you at any spot, stop me.
Nope, you still got me.
Okay, so finally y prime. I could use y prime the whole way if I wanted.
Yeah, I do the y prime.
Yeah, although sometimes with implicit differentiation you do have to be careful because a lot of times you're differentiating with respect to time.
Okay.
And so knowing what that denominator is important. This doesn't tell it to me. That's why I use dy dx, because that could have been dy dt, and y prime would You wouldn't be able to know. Okay, so this is going to be 1 minus secant squared x plus y, all divided by secant squared x plus y, the coefficient on the dy dx. And let's simplify that, only because I can, and I can make it rather significantly simplified.
Mm-hmm.
In other words, that I can take out. What does that become?
Oh, you're doing that part. Okay, I thought you were just dividing out secant squared the x plus y. Well, 1 over secant
Well,
squared.
that was the last step, was I divided both sides by that to get this.
Yeah.
Now to simplify that, I'm going to split it into 2 fractions.
Okay.
First fraction is 1 over secant squared x plus y. That's the same as cosine squared x plus y. And the second part, this part here,
secant over 1.
is 1.
Alright. Okay.
So I was able to simplify it dramatically. Now, whether that was needed or not, I don't know, because this is y prime, okay? And they've asked us to evaluate it or come up with the equation of the tangent line.
Evaluate.
One second.
Yeah.
Hello? Yeah, hi, Amy. Sounds good. Listen, I'm in a session right now, so that's okay. I'll call you back in 15 minutes. Yeah. Okay, thank you. Bye-bye. And cosine squared of x plus y minus 1 is equal to what? That actually can be simplified also using trig identity.
Really?
Uh-huh. That's sine squared. In other words, sine squared plus cosine squared equals 1.
Oh, okay. Oh, yeah, cosine squared minus 1. Right, okay.
Hold on, just a second. I might have it backwards here. Cosine squared equals 1, which means cosine squared minus 1 is actually equal to minus sine squared. So that's equal to minus sine squared of x plus y. And again, it's not really critical that I simplified this.
Yeah.
Because they just asked us to evaluate it. In other words, I could have plugged in 0 plus 0 up here to figure out what it was. But after I've simplified it, when I plug in 0 plus 0, well, what's the sine of 0 squared?
0.
Right.
Oh, wait, no, that's a lie. It should be 1.
Actually not.
Really?
The cosine of 0 is 1.
Oh, okay.
So this would be 1, but then 1 minus 1 would be 0. So y prime is 0. The slope of the tangent line at the point 0, 0 is 0. It's a horizontal line.
All right. Okay. The next problem we had to do, or one of the next problems, was we had to find the slope of the tangent line to the graph at the given point.
Okay. Which is the same as saying find the derivative at that given point.
Okay, all right.
The last problem. When you evaluated it at the given point, that was the same thing as finding the slope. First derivative is slope.
All right. Okay.
What's the function?
And it's x squared plus 4, and that's in parentheses. Well, the y equals actually isn't there.
No, that's okay. I realized that was going to be the case as soon as I wrote it.
Times y, just y equals 8.
Okay, so let's find dy dx implicitly. What are we going to have to use to do that part?
Well, the chain rule.
First, the product rule.
Oh, okay.
Because we have a product. We have that times a different function.
Okay.
Okay, so the first thing we have to realize is we're going to have to use the product rule. And then we probably are going to have to use the chain rule to do this one. But let's do the product rule first. Let's differentiate the left side. And the way I try to do the product rule the same way each time. In other words, the product rule is u v prime plus u prime v. I always try to do it that way, even though the other way is also correct. In other words, u prime v plus u v prime is just as correct. But if you're constantly doing them different, it's going to be just harder to work with it. I firmly believe in the principle of always do it one way. And the way I do it is to always start with that.
Right.
Okay, in other words, always start with u.
Okay.
So the first thing I'm going to write is x squared plus 4, and I don't have to differentiate that or anything because it's u.
Yeah.
Now I got to differentiate this. What's that? With implicit differentiation. 1 what?
Oh, 1 y prime or d by dx.
Exactly. In other words, because it's a variable other than x, if I had run into the variable r, then I would have to follow it with an r prime. If I had to run into the variable s, I would have had to follow it with the s prime. If I run into the variable x, I don't need to follow it. That's the only variable I don't need to follow it with.
Okay.
Okay. All right. That's the first part. What's the next part?
And then it's going to be plus 2x.
The derivative of that, which indeed is 2x.
And then times y.
Right. And the right side?
0.
Next step?
Gotta subtract over, well, I guess you would subtract over the 2x times y.
Correct. And finally, the last step.
Just divide that x squared.
Now, the one thing about implicit differentiation is you almost always end up with an answer that has both x and y in it. Okay, so that's why when they say evaluate it at a given point, they give you both the x and the y point. What was the point we were supposed to evaluate it at?
2, 1.
So we're going to plug in the 2 for x and the 1 for y.
Okay.
So that's minus 4 over 4 plus 4, 8.
Yep.
Minus 1/2, that's the slope of the tangent line at that point.
Okay.
Now, if they told you to evaluate it only at x equal 2, we would have to go up and solve that for y. In other words, we would have to figure out what the y coordinate was. But we could do that. We have an equation in x and y right there.
Yeah.
So if I told you that x is equal to 2 and I didn't give you this point here, you can easily figure out that y has to be 1. In other words, 8y is equal to 8, y is equal to 1. So even if they don't give you the y coordinate, you can always figure it out. But most of the time they give you the y coordinate. Oddly enough, I'm not sure why. It would be a harder problem if they didn't give it to you.
Okay. Alright, so yeah, that was all I wanted on implicit differentiation. But the next thing is it's inverse.
Okay, go ahead.
And the equation is, well, basically it asks you to verify that f has an inverse, then use the function f and the given real number a to find f to the -1 of a.
Okay.
And the function is x cubed plus 2x minus 1. And the point is 2.
And the what is what?
The real number is 2. Or pointer.
And read the problem again. What do they want to know?
Okay. It's really wordy, but
Yeah.
verify that f has an inverse, then use the function f and the given real number a to find f to the -1 or f negative prime. I don't know that. Times.
Now that means inverse.
Okay, all right.
Okay. It doesn't mean to the -1 exponent, and it
Right.
doesn't mean first derivative.
Okay.
It means inverse. Okay. And typically, the rules we use for solving for the inverse are rather straightforward. We switch the variables and solve for y. Well, notice what happens if I do that. In other words, if I call that y instead of f of x, and I switch the variables, I've got x equal y cubed plus 2y minus 1. Now notice how hard it is to solve for y.
Yeah.
So we can't do this like a normal inverse problem.
Oh. Okay.
In other words, this is a calculus problem, not algebra. It's not a precalculus problem.
All right.
In pre-calc, we would normally be able to solve these. And in fact, if it's anything other than a cubic, we could solve it. But there's a calculus. Where do you go to school, Brent?
Arvada High School?
Because I only run into this problem maybe once every 3 years, and I have about 10 to 15 calculus students every year.
Really? Wow.
And it's not an easy problem to explain or even talk about. I'm not sure I'm going to be able to do it in 5 minutes, but
all right.
Tell me if this sounds familiar, if I'm on the right track. If I multiply f of x by f prime of x, what do I know that has to be equal to?
Well,
excuse me. The definition of inverse is f of f prime of x has to be equal to what?
I have no idea. Well, it's something more than f.
X, always.
Okay.
In other words, if you take the composite function and instead of saying, remember when you had all those problems, f of g of x?
Oh, yeah.
That's a composite function. Well, in this case, if I were to try to take f of the inverse, by definition, that has to equal x. Okay? And, or f inverse, excuse me, I wrote prime there, I didn't mean to. I meant to write inverse. Okay? And likewise, the reverse is true. If I take f inverse of f, that also has to equal x. That's kind of the definition of inverse. Remember when they would say, okay, tell me if these two functions are inverses of one another. What you did was took the composite and proved that it equaled x. As long as it equals x, then it shows that this is the inverse of this.
Okay.
So starting with that definition, differentiate both sides. Well, we're going to apply the chain rule to differentiate that. The chain rule is the derivative of the outside times the derivative of the inside. Wow, how do you write the derivative of the inverse? Gosh, never had to do that before, even every 3 years. And the derivative of the right side is just 1, right?
Okay.
So what ends up happening here is you end up with the equation for f inverse. I don't have enough time to go through this whole problem, but you end up with something that looks very much like, I'm afraid to write it because I don't think I have it exactly right.
Right, okay.
I'm missing something here. What did I do wrong here? If I take the derivative of both sides, I take the derivative of the outside, which is that, times the derivative of the inside, which is that, which is notation I've never seen before for some reason, and it's all equal to 1. And then if you solve for this, you end up with 1 divided by this, or something to that effect.
Okay.
And then you kind of go from there. I'm happy to tutor you on this problem, but I'm going to have to look it up in my book to make sure I have all the specifics right.
Okay.
So I know that probably didn't help you. If you need this for classwork tomorrow or something.
Actually, I don't. I have a few days to look at this.
Good.
No.
If we have a session and, before you have to go to class, I can help you more on this. I will review this.
All right.
I can tutor it better. And there's another very hard step to it. It's not just solving this equation.
But of course.
It's also assuming that when you talk about inverses, you switch the domains and the range. So, and you have to make that assumption to figure out what f prime of x is, or something. Like I said, I'm going to have to review it. I don't have time right now to do it, but that's an impressively hard calculus class you're taking.
Yeah, and it's only AB, so I can only imagine what the BC students are going through.
They're going beyond the Common Core. Just to let you know, this problem is not a Common Core problem. You will not find this problem on the AP Calc exam, but I do run into it every now and then, usually in an IB program. Did you take IB? Were you part of the IB?
Yeah, it's an AP class, but...
Right, and I know that you lose the IB program once you get to the AP Calc. But this is the kind of problem I would run into with IB pre-calc students that were into calc, just because the IB goes above and beyond. And I don't see it very often. But I will be prepared to talk about it next time I talk to you.
Okay.
Okay? All right, Brent, I got to go. Talk to you next time. Bye-bye.
All right, thanks for your help.